So the first talk is about distributing keys and random secrets with constant complexity by Benny Applebaum and Benny Pincus. And Benny will give the talk.
Thank you. So this is a joint work with Benny Pincus, and let me mention that we have a very nice crypto group in Tel Aviv, and we're looking for postdocs, so if someone is interested, please contact me. So let me start with a motivating example. So I'm going to tell you about threshold signatures in a blockchain setting. So we have n servers, and there's a public bulletin board, and later we'll define exactly what it means, but for now, just think about it as a public board. And we start by running what's called distributed key generation, which is really an extensively studied primitive. So what does it do? It samples a random secret, delivers a sharing, secret sharing to the servers, and publishes on the blackboard, say, the secret raised to the exponent of some public group element. Okay? In addition, typically we also assume that this thing outputs also commitments to the shares. Now comes a client from Milano, and with a message, and they ask the servers to sign on this message. And for these slides, I use the BLS signature schemes, but this can be generalized to other schemes as well. So each server here computes some local signature based on his own shares. In the case of BLS signatures, you hash the message and raise it to the power of the share, plus some zero-knowledge proof that shows you that the computation is consistent with the commitments to the shares. And now the user downloads all these commitments, check that these things are okay, maybe some of them turn to be bad, throws them away, and assuming that he has enough valid shares, he applies the linear decoding in the exponent and gets signed the message. And now comes another user. Who's this guy? Who knows? Umberto Eco. You're a true local. Alon. So I was, hesitating whether to put Alon or Umberto Eco, two famous millennials, but I chose. So Umberto Eco wants to verify this message, so he downloads the public key, and now he can apply the standard verification algorithm for the signature and accept or reject the signature. So in this big system, the most expensive part is this protocol. And the reason is that in recent applications, the number of servers is typically very large, thousands, even tens of thousands. And this protocol is interactive, it requires coordination. All the other parts in this system are actually non-interactive, right? They have a single message kind of structure. And for this, we need actively secure protocol. And you would maybe think that this happens once and for all, but this is not the case. You apply it every time that you want a key refreshing, which is quite occasionally in modern systems. So we want to minimize the communication of this thing, and standard solutions typically have communication which is quadratic in the number of parties. And in fact, I'm not going to talk about this problem anymore. I'm going to talk about a more basic problem, which is this, we just call it distributed secret generation, where we just want to generate the secret sharing of a random secret. Okay? And we're going to work in what's called the ramp setting, where we have two thresholds, one for correctness and one for privacy. So say a third fraction of the parties cannot learn or bias the secret, and the larger fraction, maybe, I don't know, half of the parties, any half of the parties, a fraction of the parties can recover the secret, right? So you can think about the different thresholds. So although this primitive was not studied that much, it's actually a very natural primitive. It's also useful in MPC. You can think about it as a distributed version of committed coin tossing. It forms the information theoretic core of many threshold crypto systems. And once you have this thing, you can easily upgrade it to this DKG problem. And if you're familiar with the verifiable secret sharing, we heard it in the previous session, then in verifiable secret sharing, you have a dealer that generates a secret sharing scheme. Now we don't have a dealer. So we kind of collectively generate this secret sharing. So it's, I don't know, natural relative obviousness. So ideally, I want to get a solution that has only constant communication per party. Okay, constant, I mean that doesn't go with the number of parties. Okay, it can go with the security parameter. So the standard solution to this problem is by reducing the problem to verifiable secret sharing. So let each party choose its own secret, apply a VSS, right, generate a secret sharing, and now we can sum up the local shares, and by using the linearity of the scheme, this thing will work. So this will give you communication which is linear per party. And you can optimize it a little bit, say when you have many secrets, you can do non-trivial things, but this is not, less relevant for the DKG application. You can also use the small committee and do this thing over the committee, but this also has several drawbacks, including the fact that some party is going to talk a lot. So just to summarize, in all existing solutions, we have the following information bottleneck. So at least some parties are going to influence a constant fraction of the other parties. And this means that if your protocol has constant number of rounds, it cannot have constant communication, right? Because a protocol with constant number of rounds and constant communication, each party can influence only a constant number of parties. Okay. So in this talk, I'm going to show you how to bypass this lower bound by exploiting this bulletin board. Okay, so since I'm going to exploit it, let me define it more precisely. So we think of this bulletin board that's composed of sectors, and in each sector we have many cells. So each party has its own sector, and it has write access to its own sector, okay? And it has read access to everything, right? So you can read everything from the board. And the protocol is going to specify what every party should write and read at each point. And of course, the adversary can read everything, right? I mean, so the adversary is not restricted to this thing. And we could abstract this thing by a broadcast, right? Whenever you write, let's just say that you broadcast this value. But the thing is that when you use this bulletin board, the abstraction, you can get a more refined notion of communication complexity. So I can count the number of writes and reads, instead of just assuming that whenever I write something, everyone has to listen to it. Okay. So our main theorem shows that you can get a distributed secret generation or distributed key generation, constant number of writes and reads per party. Also, in terms of computational complexity, each party is doing only constant number of arithmetic and cryptographic operations. The protocol has constant number of rounds. If the field is large, meaning super polynomial in the number of parties, then we can support arbitrary constants here. If the field is binary, then there is some gap here, like we have some universal constant that can be used. And the crypto that we use is actually very basic, essentially commitments and zero-knowledge proof for very simple languages like linear relations over commitments. Okay, so these things are very cheap to realize, say, based on discrete log assumptions. There is one caveat. There should be. Right, when you want to decode the secret, you read a constant number of elements per party. That's clear, but you also have to read a linear number of elements from the bulletin board. But we can show that this is necessary. So in order to bypass this information barrier, you have to rely on some additional linear amount of reads from the bulletin board. Furthermore, this drawback is not that terrible because in the DKG application, you read from the blackboard and from the bulletin board anyway, right? I mean, you read the commitments from the bulletin board. So the overhead is not large. And finally, you can amortize this thing over many signatures, right? I mean, you read it once, and then you have this information. This information does not change anymore. Good. So let me briefly tell you about the proof. So previous solutions used the Shamir secret sharing, and we're going to deviate from this approach and going to use a special Taylor secret sharing scheme that will, with some special properties that will be useful in our context. So let's see. So we want to sample a random secret sharing of a random secret and want to do it in a communication efficient way. So, you know, ideally, kind of the naive thing would be like maybe we can have a secret sharing scheme in which each party just sample its own share locally and that's it. Now, of course, this cannot happen, right? I mean, because correctness means that the shares should be correlated, right? They should lie on a low-degree polynomial or more generally on a low-dimensional subspace. The idea is to let parties sample these shares locally, but then publish some public information that depends on all these random shares on the ledger. And now, given this value, this thing becomes correlated, okay? And like think in terms of coding theory, think about sampling a random vector and then publishing its syndrome, okay? So technically, it means that we are not working with linear secret sharing, we are working now with affine secret sharing. And this step alone already allows us to bypass, in principle, this information bottleneck. Okay? Of course, we are not done because we need a protocol, a secure computation protocol, to compute this public header, and we want to do it in a communication-efficient way. So for this, it will be very convenient to have a local mapping between these shares and this output, right? I mean, and local, I mean that each entry here depends on constant number of inputs here, and each guy here affects a constant number of elements in the header. And this can be done by using LDPC-based construction, right? I mean, we already used it in a previous paper. This construction is slightly different, but it's closely related to the previous one. So, we publish all these linear values, and the secret is going to be some linear combination of these shares. Think about it as a random linear combination for some random coefficients that are public. And we can show that this thing actually achieves very good parameters over a large field. In fact, as a secondary result, we also proved a new nice result about LDPC over large fields. They are nearly MDS codes in a sense. So once you have this structure, you have a passively secure information theoretic protocol for computing the thing. If you want active security, you can use commitments and zero knowledge, basically the GMW, a refined version of the GMW protocol, to get an actively secure solution with abort, okay? And the abort is the main problem that is left to handle. So imagine that we have some adversary that corrupts this server, and this guy just refuses to participate in this computation. So we can deal with this by using two different approaches. The first approach is to simply recompute this value. So, we can detect this problem. So all the honest parties decide to set the share to 0, and then they're going to recompute all these outputs when this thing is restricted to 0. The problem is that while we compute the other value, maybe the adversary aborts this guy. And the adversary can kind of use a chain of aborts in a way that will increase the round complexity to linear. Okay, so the communication is still good, but the round complexity will be too large. So that's too bad. A different approach is to assume that we have some robustness property. So what do I mean by this? Say that this guy aborts. So let's just give up on this value. Okay, let's just forget it. So know that this effectively means that some of the honest parties are being kind of excluded from the computation. For example, in this guy, its only output is this guy, is this value. So once we kind of gave up on this thing, we also gave up on this party. So we have to update this linear mapping, and we can show that as long as the number of erasures here is sufficiently small, we can somehow handle it. So this can give you like a constant round protocol, basically a 3-round protocol, but now you get a poor threshold. So in order to get an almost optimal threshold, and a constant number of rounds, we're going to combine these two approaches together. Basically, when we have many aborts, we are going to continue and recompute values until the point where we have a small number of aborts, and then we are going to rely on the resiliency. Okay? And you can show that this leads to constant number of rounds. There are some complications because this information about which party is aborted is not public information, right? I mean, if you do things in a communication efficient way, some parties don't know that other parties aborted. Okay, but this can be handled if you're careful enough. So let me conclude. We have a construction of distributed key generation and secret generation with a constant communication computation. We use new secret sharing schemes, and it's interesting that affine secret sharing schemes suddenly are useful. Like typically, we can always use linear schemes without loss of generality. I didn't mention it, but we also formalized this DKG and this DSG primitives, and we're using an MPC-based framework. And when you try to do it in a general way, like without limiting yourself to a single secret sharing scheme, this is somewhat subtle, but it can be done. And finally, this whole question started from a practical question. So I think that some of this solution in the paper may be practical. The resiliency is very poor. So the things, at least in the bounds that we get. So the resilient variants are not very efficient right now. But maybe identifiable abort is good enough if you have some punishment mechanism that you can use. So that's it. Thank you.
Any questions?
So just a tactic question about this bulletin board. I thought you said that each region has a fixed writer, so only one person can write. But somehow when you wrote this thing, you started to take sums.
Everyone can write. Just, my slide, I looked at the first party. So everyone can write, but it can write to its own area. So I cannot write on your messages, let's say.
Oh, so when you compute like sum, in some of the pictures you wrote like sum of 3 values. If only one person can write in that cell which computes the sum, so how do you actually do computation on the bulletin board? If every cell is computed by only one party.
So I'm not going to compute the sum. I mean, the sum itself is not going to be
I see, it's not written
explicitly. I mean, you're going to have enough information on the bulletin board such that when you read it, you can recover the sum and nothing more than that.
And it's only constant, so it's not a big deal. Okay.
Yes, exactly. Okay. Yeah, good point.
You said that a part of the reason to think about the bulletin board as opposed to broadcasts of that sort is to separate the read and write, essentially, right? Compute them differently. If you look at vids and stuff of that, like AVID, data availability tricks, do you know what concrete efficiency do you get instantiating things that way?
No.
Thank you.
No, but I should say maybe that even if you use just the broadcast model, I mean, we didn't know how to do this kind of thing. So, but now, you know, that's actually a good question. Like, say that you have a broadcast solution, how to measure the communication complexity. Say that, you know, I transmitted 5 elements in a broadcast. Should I charge it as 5 elements, or maybe because everyone heard it, I should pay for this thing? So the bulletin board solves these kind of issues.
Any other questions? Okay, let's thank Benny again.